Now to talk about absolute dating. So our main tool that we use in absolute dating is radiometric dating. So if you remember back when we first started our chemistry unit, we talked about the nucleus and how it is that there are certain isotopes that are radioactive, meaning that they spontaneously change from what they are into something else. Well, how long that takes, we quantify with the half-life. The half-life is the amount of time it takes for half of the parent isotopes to decay into their daughter products. Okay, so how long does it take for it to for half of it to decay? Now, different systems have different half-lives. So carbon-14 turning to nitrogen-14, this is what's used in carbon dating, which is a type of radiometric dating, has a half-life of around 5,760 years. Other things have much longer half-lives. For example, potassium-40 turning to argon-40 has a half-life of 1.3 billion years, and uranium-238 turning to lead-206 has a half-life of 4.5 billion years. So what this means is we can use different systems, different parent-daughter systems, to use for different ages. Okay, so what's happening is over time, the amount of the parent is decreasing and the amount of the daughter is increasing. So we can use the ratio of the parent to daughter to figure out how old it is. If we have lots and lots of parent and hardly any daughter isotope, we know that it's very, very young. If we have exactly 50-50 parent and daughter, that means we've gone through exactly one half-life, and so on, until out here at the end, where we have almost all daughter and very, very little parent. It's not just gone through one half-life, it's gone through many, many half-lives, and therefore the sample must be very, very old. Okay, so in this way, we can actually figure out ages. Now, some things to keep in mind with radiometric dating is that we are not actually figuring out the age of the isotopes. Atoms are super old. They're as old as the universe itself. So we're not actually determining the age of the atoms themselves. Instead, we're looking at the age of particular events. Specifically, we're looking at what is known as the closure temperature. Okay, so the idea is that we have a rock with these different isotopes inside. As the isotopes decay, if the rock is solid, then it will keep the products all together and we'll get a good ratio of parent to daughter and we can figure out how old it is. But if that rock heats up enough, then it will reset the clock. The daughter isotopes will leave and we'll get a new mix of parent isotopes, and that essentially resets the clock until it hardens again. And then it starts trapping the daughter isotope again. So really, as we're looking at these radiometric dating ages, we're looking at the most recent time that the rock cooled below the closure temperature. Now, each mineral and isotope system actually have different closure temperatures. Okay, so potassium to argon in the mineral hornblende has a closure temperature of 500 Celsius. Potassium to argon in the mineral biotite has a closure temperature of 300. Fission track dating in the mineral zircon happens at around 225, and fission track dating in the mineral apatite happens at around 100 Celsius. All right, so this is a Google sky view of Point of the Mountain. So the point of the mountain that you drive around when you're heading towards Salt Lake. So here we define the top, and down there we've got the base. As we look at these and different mineral systems, we start to see something weird going on. So as we look at this, looking at the system of potassium to argon in the mineral hornblende, remember this is a closure temperature of 500 Celsius. Using this system, it says that the age at top and the age at the base are both 30 million years old. Okay, that seems fine, rocks are old. But then when we look at potassium to argon in biotite, then it claims that it's 28 million years old. So we have two different ages for this rock. Well, what's actually going on is this isn't telling us the age of the rock at all. It's telling us about different closure temperatures. So remember, potassium to argon in hornblende has a closure temperature at 500. So this rock cooled off below 500 Celsius 30 million years ago. Then it cooled off below 300 Celsius 28 million years ago. So it took 2 million years for this rock to cool from 500 Celsius to 300 Celsius. Then as we look at fission track in zircon, it says that the top is 20 million years old and the base is 10 million years old. Well, again, this is not telling us about the age of the rock, but the age of the closure. So the top cooled below 225 Celsius 20 million years ago, and then it took 10 million years until the base cooled off below 225 Celsius. Then we see a similar thing happening in apatite. Okay, so apatite says that the age is 11 million years and the age of the base is 6 million years. Okay, so this tells us that it took 5 million years for the bottom to finally cool below 100 Celsius. I hope this kind of helps you see what's going on with these different pieces, and that you can kind of get a feel for, although we are getting distinct ages, we're still kind of interpreting sequence of events. All right, here's our fourth clicker question. Radiometric dating can give the actual age of a rock. An exception to what we mean by actual age can be found in A, sedimentary and some metamorphic rocks, B, igneous rocks, C, metamorphic rocks, or D, just sedimentary rocks. Okay, for this, think about how it is that the different types of rock are actually formed, and what it is that we're actually using to figure out the ages. Go ahead and think about it, and we'll discuss it in just a bit. All right, so what we mean by actual age is when did it actually form. So for radiometric dating to work, it will pretty much always work in igneous rock because that was rock that was hot and then cooled off. Okay, so that's not going to reset the clock. But with metamorphic rock is rock that formed due to heat and pressure but without melting. So in that case, some things may go on. If it gets hot enough, it'll reset the clock. But if it doesn't get hot enough, then the clock doesn't reset. So metamorphic rock can actually be iffy. And then sedimentary rock is rock made up of pieces of other kinds of rock. So you don't know when the sedimentary rock itself formed. You know when the pieces that make up the sedimentary rock formed. Okay, so the answer is A. Okay, so the actual age we can get from igneous rock for certain, no problem. But in metamorphic rock, we could reset the time clock, and in sedimentary rock, we don't reset the time clock when the sedimentary rock forms. Okay, so we don't get the actual age for sedimentary and some metamorphic rock.